Continue on, and we're talking chapter 11, and we got into sort of the first few sort of organic type compounds, alkanes, alkenes, and alkynes. And remember, really, each organic sort of compound has a functional group, which is the part of the compound that's sort of like the important part of it and what makes it a certain type of organic compound. So we had our alkanes, which basically have carbon-carbon single bonds. And as we talked about, they have a general formula CnH2n plus 2. We have alkenes, ENE, and those definitely have at least a double bond somewhere along the way. And as we've talked about a couple of times along the way here, every time we make another bond in sort of organic chemistry, we do have to sort of sacrifice a couple of hydrogens to make sure that carbon does not end up with too many bonds. So they have a general formula CnH2n. And then we talked about alkynes there, which are carbon-carbon triple bonds. And again, adding that extra bond gets us to CnH2n minus 2. And as we've been talking about since the beginning, everything is related to the alkanes. So again, if we had something like this, that is C2H6, which is ethane. If we, again, were going to put on there a double bond, we would lose a hydrogen from each carbon, and we would end up with two hydrogens on each of those carbons and a double bond in between. And that would be ethene, ENE. And if we put a triple bond, once again, we're going to lose two more hydrogens, one from each carbon, and we'll end up with ethine, YNE, like our sort of organic class name. Now, again, these are condensed structures. Obviously, you could draw out the hydrogens there, and you can see, again, we basically lose, as we talked about, one hydrogen, for example, from each of the carbons. They don't come off with the same carbon when we put on that extra bond. And again, we lose another couple hydrogens, one from each carbon, when we put on that third bond for the triple bond, and we end up with something that looks like this. They are based off of, obviously, alkenes and alkynes. They're also what are referred to as being unsaturated hydrocarbons because they do not have the maximum number of hydrogens for each carbon. They have at least one double bond or a triple bond that happens here. Now, when we name these guys, we just kind of change the back part of the name for these guys, and that gives us really the name that we're looking for, depending on what it is. Once you get to approximately kind of four-ish or so carbons with our double bond and triple bond, as we talked about at the end, we do need to start giving the location of where that double bond or triple bond is located. In this case, it can only be really here, so it's going to be no need for any type of numbering. So if we had something like this, remember that we do just kind of follow our normal sort of naming rules. What we're looking for is the longest carbon chain. Remember that when you have a double bond or a triple bond, the longest carbon chain does need to contain that double bond or triple bond. So they got to be in the longest carbon chain. So here, if we just go straight across, we got 1, 2, 3, 4. And 4 carbons is based off of butane. Because there is a double bond again, it becomes butene, ENE. And now we do need to give the location of that double bond. And unlike alkanes, where the priority in terms of the numbering goes to the groups that are attached, when you have a double bond or a triple bond, the priority in terms of numbering the carbon chain is to give the double bond or the triple bond the smallest number. Now, in this particular case, we could go this way, 1, 2, 3, 4, or we could go on the bottom there, 1, 2, 3, 4. no matter which way you go, you are going to end up with that carbon-carbon double bond at carbon number 2. If you go in this direction, it's at number 2. If you go in this direction, it's at number 2. So in this case, it's actually a tie in terms of the numbering for the double bond. So if that does happen, the next important thing is actually the groups that are attached. And the only other group we have here is a chloral group. And since there is a tie in terms of the numbering for the double bond, the next important thing would then be that group. And you could probably just see going in the left direction here, that group would then end up at carbon number 1, versus if you went in the right direction, it would end up at carbon number 4. So in this case, because the double bond's a tie, we then default to the group, and we would want to go in this direction again to give that group the smaller number. And I'm sorry, that's not carbon number 1 in that direction, not 2. So what we would have here is 1 chloral dash 2 butene. Once again, the 2 is the location of the double bond. The 1 is the location of the chlorine on the carbon chain. Any questions on that there? All right, so again, we just kind of follow our rules. And like I said, like the longest carbon chain has to have double bond or triple bond in it. And once about 4 or more carbons, usually you got to start sort of giving locations of where that double bond or triple bond is located. Any questions on the stuff we talked about last time? All right, so I don't think we did these, so why don't we give these a try? Let's do some names here. This one here is just go straight across, looks like it's your only option, really. So that is 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, 6 carbons, 7 carbons, and 8 carbons. So 8 carbons is based off of octane. It has a double bond, so becomes octene. In this case, we do need to give the double bonds location, and you can probably just visually see if you go left to right here, that is definitely going to give us, bless you, a smaller number for that double bond than going in the other direction. So that's going to be carbon number 3 where it starts, and that would be 3-octene. Yeah. Any questions on that one there? All right, taking a look at the next one here. We have 1 carbon. There is another carbon right about there on the other side of the triple bond. 3, 4, 5, 6, 7, and 8. Your other option would be 1, 2, 3, 4, 5, 6, 7, which looks a little bit less in terms of what we're looking for. So 8 is our kind of only option there. And by the way, as a reminder, in this case, again, it is not longer to do this, but you cannot go this way though. 1, 2, 3, 4, 5, 6, 7, and 8, because now you've avoided the triple bond. So remember, the triple bond or double bond has to be part of the chain. So that is, again, not an option in this case. So we're going to go, it looks like 8 straight across there. So we'll do that there. So here we got 8, which again is going to be octene. Not octene, octine, YNE, because it is a triple bond in this case. Octine. Location, as you can probably see, is going to be 1, is going to be our shortest move there. Again, 2, 3, 4, 5, 6, 7, and 8. So this is going to be 1 octine. We do have a group here, and this group is a 1, 2, 3 carbon group. A reminder, I think, as there was a question last time, this carbon right here is part of the main chain. So again, you don't count it as part of the group there. So that's the 3 carbon group, which is based off of propane. And that's going to be a propyl group, right? We put YL at the end of it. And it is hanging there, as you can see, at carbon number 4. So that's going to give us 4 propyl, 1 octine in this case. Any questions on that there? Now you can see in this line structure, especially with the triple bond, it's drawn kind of straight. And that is because when you do have a triple bond, the geometry of it, like we talked about with Lewis structures, is if we look at this carbon, that is one electron pair, two electron pairs, and also one and two bonds. And if you remember, two electron pairs with two bonds is a linear geometry, 180 degrees. So that is why it's shown kind of straightly drawn out in that case. By the way, also with a double bond, the geometry does change from what it is in an alkane. With a double bond, if we were to look at, say, one of those guys there as well, if we were looking at this carbon here, it has one electron pair, two electron pairs, and three electron pairs. Bless you. And it also has one, two, and three bonds. And again, in terms of geometry, when you have a double bond around that carbon, three electron pairs and three bonds is trigonal planar, that sort of triangle type of shape with 120 degrees. So remember, with all single bonds, we have that tetrahedral 109.5, which is typically why most of the line structures are drawn that zigzag shape because of that. But the geometry of the carbons do actually change when you put double bonds or triple bonds on it. Personally, for me, I don't really care if you show it. If you do draw a line structure, if you want to lay up a triple bond like that, it's all good. But you will sometimes see in books it drawn straight out because of that. And because of that as well, people often miss this carbon right there. Yeah, as they're counting, they just kind of jump to the next little. A lot of times when people are counting, they just kind of jump to the next one past it. So you don't want to miss that carbon that's on the other side of that triple bond and stuff like that. Any questions on that there? Let's take a look at maybe here. So obviously we talked about that. Let's take a look at a couple more here. Why don't you also draw? Let's see. Let's do. Two, and, let's see. Why don't you draw 4-bromol 2-hexene? Why don't you also draw? Let's do 3. We'll go 3-methyl 1-pentyne. Hope for the best. See how we do. All right, guys, on the left there are some names, and on the right there are some structures. Let's see what you come up with. Okay, let's take a look, see how you're doing. We'll start here with the ones on the left. Longest carbon chain has a double bond in it. 1, 2, 3, 4, and 5. By the way, you could also get to 5 by going kind of this way and then down as well. So that's a possible choice if you want to go that way. Once again, it doesn't really matter which way you go. If you have sort of a straight one, that's sometimes easier to see everything. So we'll go with just this one straight across here is going to be our longest carbon chain. That is 5, and it has a double bond, so that's going to be pentene, E-N-E, for the double bond. We want to number the chain to give the double bond the smaller number. Again, hopefully you could just see it that if you go 1, 2, 3, 4, and 5, that's going to give our double bond carbon number 2. If you go in the other direction, you're looking more at like carbon number 3, which again, we want always the smallest in organic. So that's going to be a 2-pentene. Now, because we're kind of locked into the numbering in that case, any group that is there would have to be numbered accordingly. And we have a one carbon group here at the end. And a one carbon group is a methyl group, right? And that then would be at carbon number 4, so a little 4-methyl 2-pentene. Yeah. Any questions on that one there? Coming to the next one, one carbon, two carbons, three carbons. Remember, there's one right there, 4, and one on the other end, 5 and 6 carbons there. Yeah. So 6 carbons is going to be based off of hexane. We have a triple bond in this case, so that's going to change it to a YNE at the end. Once again, there's really nothing else attached there, so we're just really looking for the location here of our triple bond. And again, just visually looking at it, if you could hopefully see if you number in this direction, that definitely is going to give our triple bond the smaller number, which would be a 2 in this case, and this would be 2-hexyne. Any questions on any of those names there? So if we are drawing just like normal, always just want to work backwards, right? So here, hexene, the ENE tells us there should be a double bond, and the kind of hexane part tells us we should have 6 carbons. So like normal, I would just start with the carbons. So that's 6, I think. And remember, because you're drawing it, you could actually choose carbon 1 to be on either end. I'm going to choose my carbon 1 to be over here. So for me, that's carbon 1. If you chose the other side, it's not wrong to do that. And that means that carbon number 2, that is where we should see our double bond occur, which would be here for me, as right here should be carbon number 2. That takes care of that part of the name. And because that's carbon number 2 where I put the double bond, carbon number 4 would end up somewhere in this area, which would be where I'd put my bromine. And again, at this point, I'm pretty much out of everything in the name. Remember, carbon needs 4 bonds. So at the end here, we just fill it in with hydrogens to give it 4 bonds. So the guy at the end there would need 3. This guy has 2 bonds. He would need 2 hydrogens. This guy has 3 bonds. He would need 1. 3 bonds would need 1. 3 bonds would need 1. And 1 bond would need 3. And again, that would be a condensed formula that I just drew there. If you're going to do line structure, kind of worked again the same way. Just going to start with your carbons, 1, 2, 3, 4, 5, and 6. Since I'm doing 6, 1, 2, 3, 4, 5, 6. And once again, for me, if you wanted to, that would be carbon number 2, and 3, and then 4 would be right about there. And again, you wouldn't put any hydrogens or anything like that as well. Any questions on that particular one there? Same idea here. We're going to kind of work backwards. So definitely the pentane part tells us 5 carbons. The YNE part tells us triple bond in there. So again, we'll start with our 5 carbons. And 1 pentyne, again, you can start at either end. I'm going to put it here, and that's going to be my triple bond at carbon number 1. And again, obviously, here's my carbon number 1. That would mean my carbon number 3 would be right around here, and I'll just put a methane there, our methyl group. And at that point, we're going to fill in hydrogens. So 1 bond needs 3, 2 bonds needs 2 hydrogens, 3 bonds needs 1. This carbon right here has 4 bonds already, no hydrogens on that one, right? Because it's already done. And the guy at the end has 3 bonds, which means he just needs 1 hydrogen to fill it in. And again, that would be our condensed formula. Line structure, same deal. 1, 2, 3, 4, and 5. Triple bond right about there. And 1, 2, what's it, 3. Methyl group right about there. Yeah, and stuff like that. Yeah. Any questions on drawing, naming, alkenes, and alkanes? Yeah. When you're drawing it, is that what you're asking? When you're drawing it, so for example, we started with this 1, 2, 3, 4, 5, right? So there's 5 carbons, right? It is absolutely your choice since you're drawing. If you wanted to call this guy at the end carbon 1, you could, but you could just as easily have drawn this guy as carbon 1. So because you're drawing it, you have the choice. Either end could be carbon number 1. You just, whichever one you pick, you just got to number accordingly that way. So for me, I've been picking the one on the left, but you could have picked the one on the right. And if you pick the one on the right, then that would be your carbon number one. So because you're drawing, you kind of have the option as to which one you want to call carbon number one. Yeah. Mhm. Yeah, so in these cases, if you have the structure like we did over here, uh, you want to find the longest carbon chain that contains either a double bond or a triple bond in it. And once you do, that's what I put in this first box here. Once you identify the longest carbon chain, the way you want to number that chain is based on the double bond or triple bond, whichever way gives the double bond or triple bond the smaller number. So in this case, we went this way because that put our double bond at carbon number two. If you went right to left the other way, your double bond would start at carbon number three, which would be a larger number, and you don't want that. So the priority in terms of numbering for double bonds or triple bonds is those guys are the priority. So whichever way gives them the smallest number. Other questions? All right, so let's talk about cycloalkenes, which are basically our ring structures or cycloalkanes that's got itself a double bond in it. And if we take a look at the one that's on there, we'll just kind of redraw it here. And we got a little thing happening there. We're just going to put a line there. So much like cycloalkanes, the longest carbon chain here that will contain the double bond, or even if it's a triple bond, is the ring. And this ring is a 1 carbon, 2 carbon, 3 carbon, 4 carbon, and 5 carbon ring. So once again, 5 carbons is based off of pentane. It's a ring structure, so that's cyclopentane, but it also has a double bond, so it becomes cyclopentene, ENE. Now, in this particular case, we do have a group that's hanging off of it, which is a methyl group, right? Just a line by itself is a carbon at the end with 3 hydrogens, so that's just a methyl group hanging off. Now, in this particular case, you do not need to give the location of the double bond or triple bond like we do when it's just a straight chain and we go like 2 pentene or 1 pentyne, because wherever that double bond or triple bond may be, or double bond in this case, is always going to be carbon number one. But we do want to use it as carbon number one to number the group that is there in this particular case. So if we look at sort of our option here, bless you, go that way, that way. Now we want to get this group the smallest number, and you may be tempted to go, can I just call that carbon number one and hang a left there, and it's at carbon number two? And the answer is you could, but it would be wrong because they have a weird rule that says when you have a double bond in a ring type structure and you go to number it, you actually have to number through the double bond. So you can't go away from the double bond when you're numbering. So you actually have to pass through the double bond to get to your group. So that means the way I just did it there on the left, you should not do because I did not go through the double bond. So that gives me really two options of how I could get myself to that group in terms of numbering. I could start here as carbon number one and just go clockwise, right? Two, now I'm going through the double bond, right? 3, 4, and 5. So obviously if I go through the double bond starting with that guy up there on top as carbon number one, my group's going to end up at carbon number 5. The other option is you could start at the other end of the double bond, and you could call this carbon number one, and then we would go through the double bond to carbon number two, carbon number three, carbon number four, and obviously carbon number 5 in this case. Once again, we do want to give the group the smaller number. So in this case, I should go this direction, right? That's going to give my group a smaller number of 3. And this would then end up being 3-methyl cyclopentene in this case. So that's a slight little rule you have to remember, that if you do have a double bond within a chain or a cycloalkene, you have to number through the double bond, and you could go either way, one side or the other, but you can't just kind of go away from the double bond, so your numbering has to kind of go through it. Any questions on that there? So if I had something like this, Why don't you give a name to that there? Why don't you also carbons? So that's based off of propane. There's definitely a double bond in there. So, and it's a ring. So that's going to be cyclopropene, ENE, because of the double bond. Uh, Once again, we do not need to give the location of the double bond. It is assumed to be carbon number one. We do have a bromine hanging out over here, and that means our possible numbering is going 1, 2, and 3. Again, we have to go through the double bond, or you could start over here at carbon 1, 2, and 3. And it really doesn't matter in this particular case. Whichever way you go, it's going to be carbon number 3. So 3 seems to be a winner, and that's going to be a 3-bromol cyclopropene. Any questions on that name there? How about the guy on the left? Longest chain, yeah. If you put 3-bromo 1-cyclopropene, yeah, technically you don't need it, and you shouldn't put it for this type of structure because again, it's assumed to be number one wherever it's at in that ring. Because again, if it turns wherever it ends up, it's going to be carbon number one as well. Other questions? All right, longest carbon chain over here is actually 6, I believe, right? 1, 2, 3, 4, 5, and 6. So it is definitely a double bond, also cyclic type structure. So that's going to be like a cyclohexene. Once again, we have a couple groups hanging out there. We got a chloral group there. And once again, a line with nothing at the end of it is a methyl group, right? So our options in terms of numbering is we could number 1 and 2 going in this direction, or we could go 1 and 2 going in this direction. And for me, it just looks like perhaps going clockwise there is going to get us shorter numbers or smaller numbers. So if I continue down this way, that would be 3, 4, 5, and 6 rather than 1, 2, 3, 4, and 5. So we're going to end up with bigger numbers. So we definitely want to go in this direction as it's again going to give the groups a smaller number in this case. And that means that our chloral group is at carbon number 3 and our methyl is at carbon number 4. And now we just kind of put all that together and we'll just kind of go here alphabetical first, right? So 3 chloral, 4 methyl, cyclohexene. Yeah. Any questions on that name there? So again, that's the important thing. You just got to remember in sort of a cyclostructure, people always want kind of just number to get the smallest and go away from that double bond. Got to go through it in terms of the numbering. Any questions on that there? All right. Why don't you give the name here of each of these? All right, so whole thing here is the longest carbon chain, nothing else there. That is 6 carbons, so that's going to be a cyclohexene. And again, nothing else there, so no groups to attach. Longest carbon chain, once again, going to be the ring or cyclic structure there. That is a 5 carbon one, so that's going to be cyclo pentene ENE since we have a double bond happening in both of them. Here we do have 2 lines hanging off of it, and each of them is a methyl group. That also means that within this compound we have 2 methyl groups, so we do add a prefix, right? So that's going to be a dimethyl happening there because there's more than one of the same group within the molecule. We do need to give the number, and once again, hopefully just kind of looking at it, you can see that if you start at this carbon here, and call it carbon number 1, 2, and 3, that's going to give you the smaller number. If you go in the other direction, if you go in this direction, you're definitely going to get a lot bigger than a 3 if you kind of go in that direction. They are both at carbon number 3, so remember that you do need to give the number twice, even if they're hanging out the same carbon. So this is a 3, remember, comma 3 dimethyl, and then a little cyclopentene in this case. Yeah. Any questions on that one? Yeah. They're not. Are you asking why are these this group here not an iso? Is that what you're asking? Yeah, it's not because they're two individual groups, and again, remember that this carbon right here is actually part of the chain, the longest carbon chain, so it doesn't count for those groups that are hanging off. So really, the groups part is just one carbon here and another separate group that's one carbon here. Again, because the one that they come into is part of the ring type structure. Yeah. Question. Because you do have to give the number for each group that's located, even if it is the same group on the same carbon, you have to give the number twice to indicate that they are both located there. Because the di doesn't mean that they are both located on the same carbon. The di part of the name there, which says dimethyl, means that there's just two methyl groups in that compound. They could be on the same carbon, but they could also be on different carbons as well. So because of that, you have to give the number twice, even if it's the same number. Yeah. Yeah. No, alphabetically for the group um, is how you want to put them. So you can have, and I think we had one last time where if you go alphabetical based on the group, you could have a group alphabetically that has a larger number than the next guy. And you do go alphabetically regardless of the number. But you do also go alphabetically if you have a situation like this and say there was another thing attached there or something. You would not alphabetically look at the di, you would alphabetically look at the methyl here for this one. And you do not because so we use a dash only between number and letter or letter and number. So this is basically just two letters hanging back to back, so you don't need it. But so the dash is really to kind of separate a number from a letter, and the comma is to separate two numbers that come through there. Yep. Other questions? Okay, we're going to continue on, and we're going to talk about a couple other things here. So the next thing we're going to talk about is another type of isomer. And remember, we talked about isomers in the previous chapter. And isomers, again, are things that have the same molecular formula but different connectivity. We do gain a certain type of isomer when we have a double bond involved. And that is what is known as a cis or a trans isomer. And basically, whoops, basically, cis means the same side of the double bond. And trans means opposite sides of the double bond. So when you have a single bond, within a single bond, there is what is known as freedom of rotation, which means it could rotate all the way around that single bond perfectly fine. That's why when you draw like alkanes and stuff like that, you could put the group on top or you could put it on the bottom. It doesn't really matter because it has free rotation around that single bond. When you put a double bond into place, essentially it locks everybody into place and you lose that ability to freely rotate around the two carbons and everybody gets sort of stuck into place. And because of that, you end up with groups that are near the double bond that get stuck in this particular location, either on the same side of the double bond, opposite sides of the double bond. Now, when we look at a cis or trans isomer, the possibility of having it has to come down to a couple of things, and that is when you look at the double bond, which is always the double bond you want to look at, or the two carbons you want to look at are the ones that are involved in that double bond. And when you look at each double bond carbon individually, the first thing that has to happen is each of those carbons within the double bond has to have different groups attached. So like A and B is different. So you cannot have on the same carbon within the double bond two of the same groups. Otherwise, cis or trans isomers cannot happen. You also need some different groups over here. on this carbon, use my alphabet there. So cis and trans isomers is possible in this particular case because each carbon within the double bond actually have two different groups attached. The second thing that you need for cis or trans is the two carbons need different groups attached to them, but then you need some type of group that's the same on both carbons. So here, if we look at it, the group that's the same group on both carbons is the A in this case. Yeah, there's an A on both of those carbons. And you can see by looking at their location, they are on opposite sides of the double bond. One's kind of up and one's kind of down. So this would be our trans isomer in this case, again, because those groups are kind of up or down. Now, those are, again, the two things that you need to even have the possibility of having a cis or trans isomer occur. Each carbon in the double bond needs to have two different groups attached, and you got to have some group that's the same. Now, when we do cis and trans, we sometimes call hydrogens a group. Just for the cis and trans part, it's still really not a group, but it is sort of thought of sometimes as a group. Now, if you had a double bond where, you had something like this, A there and an A there and a B and an A here, you could not have cis or trans isomers with this because this carbon over here has two of the same groups attached. So if you ever come across a situation where, again, the carbons within the double bond, one carbon in that double bond has two things that are the exact same thing attached to it, cis and trans isomers are not possible. Now, let's say we wanted to draw, say, a cis or trans isomer, and let's say we want to draw this guy down here, 1,2-dichloroethene. The first thing I would do, honestly, is draw it exactly kind of like what you see here. I would just draw it just like I was going to draw it, like I was doing, like just drawing any structure, basically. And then what I would do is I would kind of redraw it and just focus in on the carbon-carbon double bond. And I would redraw it that way. And now let's again say I wanted a cis isomer, which means, for example, my chlorines here need to be on the same side of the double bond. I can now very easily just redraw it like so, and then put my hydrogens going up. And now I have just drawn a cis isomer. If I wanted a trans isomer, I could start with the double bond, draw a chlorine down and a chlorine up, and put the hydrogens obviously in the opposite location in this case. And now I just drew a trans isomer. So if you're ever asked to sort of draw a cis or trans isomer, sometimes it's easy just to draw like normal. Once you get your structure, just kind of put a box around the double bond and figure out what your groups are, and then redraw it, starting with the double bond and just aligning your groups in either the cis or the trans orientation, rather than just trying to draw cis or trans kind of like right out of the box or something like that. Sometimes it's a little bit harder to do. Any questions on that there? And again, we have this option because we lose rotation around the double bond, so everybody just gets locked into where they're at in terms of three-dimensional space, and they can't really rotate around or anything like that. There's your fingers. So let's take a look at let's take a look at this one that you got here. So this is cis or trans is added to the name. So if we were to name this, there's one carbon here, two carbons, and again, that is all the carbons that there are. And it is a double bond, so it would be ethene. Here we do have a bromine at carbon 1 and a bromine at carbon 2. It doesn't really matter the numbering because you could go either way. And this would be one, oops, I'm not going to have enough room there. We'll go up here. 1,2-dibromo ethene. And really the only difference here is we just add cis in front of it. So cis 1,2 dibromoethene is again that. Here again, if we were counting carbons, one carbon, two carbons. And again, that's going to be ethene. We still have our two bromo groups, which is our dibromo. And again, no matter which way you number, They're both going to end up at carbon 1 and 2, so they're going to be the same number either way. But again, this is trans as they are on opposite sides here of the double bond, and here they are on the same side of the double bond, which is our cis location. So if you had to name it, or if you're given a name, sometimes they just include that in the front of the name to tell you, is cis or trans in terms of its location. All right, so for each of these, decide is it a cis. Okay, let's take a look. Let's start with the first one, A. So what you want to isolate is the double bond in order for cis or trans. And the first thing you want to make sure is this group and this group different, which it is. Is this guy and this guy different? And it is, right, from each other. Again, if you had two things on the same carbon, that double bond, you could not have cis or trans, would not be possible. Now we want to look for groups that are the same on opposite carbons, and you have your choice in this case, the chlorines, or you could look at the methyl groups if you like. Both chlorines are on the same side of the double bond, and that would make this a cis isomer. Yeah, any question on that one? Coming down here, once again, isolating our double bond. We're going to look at this group and this group. They are different. On the other double bonded carbon, that group and that group are different, which is good. And again, we're going to look for groups that are the same on opposite carbons. So I could look at the bromine, for example, and they are on opposite sides of the double bond. So this would be a trans in this case. Lastly, down here, looking at the double bond here, this guy and this guy are different, and this one and this one are different, which is good. Looking at something that's the same, that is methyl groups on both sides there, which are opposite of each other, so this should be a trans as well. How about the one thing I drew up there? What is that? Cis or trans? It is, again, different and different, different and different. Same here, right? Same here. And they're on opposite sides. This would be trans. First off, any questions on that there? By the way, if I was to name this, longest carbon chains, how many? 2, 3, 4, 5, 6, 7. Longest carbon chain is 1, 2, 3, and 4. Yes. Otherwise, everybody that has cis or trans will always be 2. That's a very popular answer because everybody just focuses on the double bond. So that's actually 2 carbons, or 3 carbons and 4 carbons with a double bond. So that's going to be butene. Location of the double bonds at carbon number 2, no matter which way you go, right? So that is 2-butene. And we also have one group, 2 groups off of it, which are 2 chloral groups. So this is actually cis, right? Put the numbers there. Cis 2,3 dichloral for the locations of those chlorine groups. 2-butene. So that's really important to make sure that if you did need to name it, and it is drawn in either cis or trans, that you pick up on all the carbons. Again, it's a common error. People kind of just focus on the 2 middle ones. And like I said, everybody ends up being just 2 along the way. Same thing here. If we were going here, this is 1, 2, 3, and 4 as well. Also butene. 1, 2, 3, and 4 as well. Also a butene as well. How about the one I drew? Longest carbon chain is? One, two, three, four, five, six, 7, and 8. Yeah, so that is going to be a octene, right? Location of the double bond, 1, 2, 3, 4. 1, 2, 3, 4. It really doesn't matter which way you go. You're going to hit 4. That's that double bond. So this is a 4-octene and a trans. 4-octene in this case. So again, that's really important. Again, if it's drawn like kind of showing the cis or trans, you just got to make sure you pick up on that longest carbon chain as well. Now for cis and trans, we kind of, again, like I said, sort of count hydrogens almost as a group, but when you go to name it, it's normally like hydrogen. It's not a naming part of group or anything like that, but just for what's there. Question are cis or trans isomers there. All right. Let's then talk about reactions that alkenes undergo. And alkenes undergo addition reactions. And pretty much addition reactions all occur the same way. And when we talk about these reactions, you just want to kind of remember the general way it happens. And with alkenes, pretty much this is the deal. You have a double bonded guy. And it really doesn't matter how many carbons you got. The only thing that changes is the double bond part. So you could do whatever you want. You're going to add something to it. We'll call it like an AB type thing. Now, when we look at the carbons on the left there, right, in our original structure here, every single carbon, right, has 4 bonds, which means addition, we're going to actually put both of these things, both of these guys get put on. So we cannot just put those guys on because each carbon will end up with too many bonds. So we have to make room for those guys that are coming in to actually bond and not end up with too many bonds. So what always happens in this case is this, and you should not overcomplicate it. This double bond becomes a single bond. And by making it a single bond on the other side, we now have room for those guys coming in to bond without ending up with too many bonds. So literally, you should just always copy exactly what this looks like. And the first thing you should do is just turn it into a single bond. So I'm not going to get fancy with it. I'm just going to copy exactly the way it is and just basically turn my double bond into a single bond. Yeah. Now, once you do that, the way that these things get added on is one goes to one carbon and the other goes to the other carbon. They never add to the same carbon. So one to one and one to the other. And for example, here we'll put the B over here and the A over here, and that's it. Yeah. So it doesn't matter if there's 400 carbons attached to that thing or not. It's just the double bond that changes. Double bond into a single bond. Add both things into it. Any questions on just the general way that reaction occurs? And that's always the way it occurs in this type of situation. So when we look at these type of things, there are some things that get added in. There is a type of reaction which is known as a hydrogenation reaction. Hydrogenation reaction involves hydrogen. And this is sometimes referred to as a symmetrical addition. And what it means by symmetrical is you're adding the same thing to each carbon, so you can't really screw it up. Each carbon just gets the same thing, basically. So if we had an alkene like this, and I'll just draw it out here. We'll just draw a fun one here. Maybe not too fun here. Do a little bit of that deal. And a little bit of that deal there. And yeah, we'll do that right there. And here I'm going to add hydrogen to it. And hydrogen is H2, which is basically 2 hydrogens. So if I were to do this reaction, absolutely the only thing I should worry about is where that double bond is. This is the only thing that's going to change. And once again, the only thing that's going to happen is the double bond will become a single bond. So I'm going to basically, if I'm smart, I'm going to basically just copy what's there and change my double bond into a single bond without overthinking it, because basically your answer is sitting there right there on the left-hand side. You should absolutely just copy this as fast as you can without thinking too much. Sometimes thinking, not good in these situations. And just copy exactly the way it is. The only thing you have to remember is when you get to the double bond, make it a single bond, yeah? And pretty much you now have 99% of your answer done by just copying the original thing, okay? Now, where we took the double bond out, that is where we're going to add in each of these hydrogens. So I'll do it in different colors so we can kind of distinguish. So we're going to add in a hydrogen to one of the carbons that was in the double bond originally, and we're going to add a hydrogen to the guy on the right-hand side that was in the double bond originally. We go from an alkene to all single bonds here which is an alkane. Yeah, so we go from an alkene to an alkane in this case. And we had 1, 2, 3, 4. We have one butene here, to butane in this case. This is what is known as a hydrogenation reaction. Perhaps you've heard of partially hydrogenated things. Yes, that is what they do. They take out some of the double bonds, throw some hydrogen in there, and it becomes more single bonded. What does that do? It makes something like oil, which has a lot of double bonds, become something like margarine, basically, and stuff like that. So that's that process that occurs there. Question on that. Again, doesn't matter if it's something like this. Doesn't matter if it's like this deal. What is the only spots it should change? Where our double bond is, right? And our double bond should just become a single bond, right? So once again, I'm just going to copy what's there, except and get rid of the double bond. In this case, we are adding two hydrogens. And by doing so, originally, just so you know, right, originally in our original structure, there is one hydrogen there to begin with and one hydrogen there to begin with, not usually drawn on the line structure there. And now these two hydrogens will add in the same location. So I'll do it in maybe a different color here. We'll put a hydrogen here and a hydrogen there. You really honestly on this one don't need to actually draw the hydrogens because it's line structure, so you could actually just draw the ring and you would be fine in this particular case, but nothing else changes in this case. And there is still, these two hydrogens are still there, by the way. Yeah, they're still there as well because carbon still needs 4 bonds, which means there is still those original hydrogens there as well that gives that carbon now 4 bonds. Again, we go from a cycloalkene to a cycloalkane in this case through a hydrogenation reaction. You can also do this reaction with a halogen, works the exact same way. Also a symmetrical addition, so if I had something like this, do this, do that, do that, do this. And let's just say I added Br2 to this. Why don't you draw what you think it will be? So that's basically 2 BRs you're adding on. Yeah. Okay, so once again, this should be your only source of focus, and that's the only thing that's going to change to start with. Again, we're just going to make it into a single bond to have room for everybody to come in. Again, I'm just going to copy. Let's go in here. I'm going to go below it so I don't run out of too much room there. And again, I'm just pretty much copying what's going on there. When I get to my double bond, just going to turn it into a single bond now. And again, everything else is going to be the same. At this point, we have now basically made room for those two things to come in. And as we've been talking about, they do go to opposite carbons. And this is called a symmetrical addition because you're adding two of the same. So again, you can't hopefully mess it up as long as you put them on different carbons. We'll throw one bromine there and we'll just throw one right about there as well. Any questions on these symmetrical additions? Now, sometimes you may see written up on the arrow, something like platinum or a catalyst. It has nothing to do with the reaction. It's just there to speed it up, so you don't really have to worry about it. But sometimes you'll see some things written on the arrow as a catalyst that's necessary for these reactions to take place. Any question on those addition reactions there? Now, these are symmetrical additions. There's also what is sometimes referred to as unsymmetrical addition. And unsymmetrical addition basically means we're adding two different things to the double bond. So, for example, one reaction is known as a hydration reaction, which means we're adding water. And when water is sort of used in this reaction, you can think of water as H and OH is sort of how you could think of water, how it adds. It adds sort of like that. It will add an H and it will add an OH is sort of how water will be put onto the double bond. So if we take something like this, we'll just do, yeah, we'll do one more for now. And let's say we did add water to it in a hydration reaction. Once again, as I mentioned, this is essentially how water is added, OH and H. Again, nothing much changes from the other. We're still going to focus in only on the double bond here. And just like we did previously, we're going to turn this double bond into a single bond to leave room for it. And in this particular case here, we will start with just redrawing it. And again, I'm going to go a little bit lower there so I don't run out of too much room here. Just going to redraw it here. Again, turning my double bond into a single bond there. And everything else is going to be the same. Now, in this particular case, you will end up with the hydrogen going to one and the OH going to the other in this case. And in this case, it doesn't matter where you put the hydrogen or where you put the OH, you will end up with the same compound. Now, we go and now create what is known as a alcohol that has a functional group of OH. So we go from an alkene and we make an alcohol in this case. And this alkene here is 1, 2, 3, 4. That is like 2 butene. Yeah. To name the alcohol, not surprisingly, works kind of the same way. We're looking for the longest carbon chain that has the OH group on it. 1, 2, 3, 4 that has the OH group on it. So alcohol ends in OL. So instead of butane, this is butanol, OL at the end of it for the alcohol. And alcohols also kind of like double bonds and triple bonds. Once you get past 3 or more carbons, just like the double bond or triple bond, you have to give the location of where the OH is at. And you want to give the OH the smallest number, which in this case would be going in this direction, 1 and 2. Obviously, if you went this way, 1, 2, and 3. So 2 is the right way. And this would be known as 2-butanol, which is an alcohol. And just like double bond, triple bond gets the priority when you have an alcohol, the OH group always needs to be numbered the smallest way. So that's how it basically works in that case. Question on that? Yeah. If there's a second, you won't have any of that here. So you'll only have one functional group in your molecule. So whatever the functional group always sort of gets the priority in terms of numbering in most cases. Yeah. Other questions? Um, Now, in this particular case, the reason why it doesn't matter where you put the OH or the H is if you did it the other way and you drew it like this, and we ended up putting the OH here and the H here, and again, obviously we have all the other stuff the same. If we were going to name this alcohol, again, you would do your longest carbon chain, which would be 4. So that is butanol, OL. And we again want to give our functional group here the smallest numbering, so we would number 1 and 2. And what did we end up with? We ended up with the same name in this case, which means it's the same molecule just turned around, and it is not anything different. So that's why in this case, it doesn't matter. The real reason and why you know it doesn't matter is it actually has to do with the carbons that were in the double bond to start with. And when we look at each of these carbons here in this double bond, how many hydrogens does each one have directly attached to it? Carbon on the left has how many directly attached to it? Hydrogens it has directly attached just one, right? Because this is a carbon that's attached to it, right? So this has one hydrogen attached here. This carbon right here has one hydrogen directly attached to it. So when you have a double bond that has the same number of hydrogens attached to it, and you have this unsymmetrical where you're adding two things, it doesn't matter where you put them. It will end up being the same compound every time. But if you have a difference in the number of hydrogens there, it does matter. So let's take a look at an example of something like that. Let's see here. Let's do this. And let's do this. And let's just do... Actually, let's just do this. Make it easy. Go that way. That should work. So if we're doing this and we're going to add our water in this case, in this hydration reaction, again, it's going to add as HOH in this case. Once again, let's just draw the structure here. And first thing I should do is double bond, right? Turn it into a single bond, right? So again, we're just going to copy exactly the way it is and turn it into a single bond. And I have too many hydrogens on that, so let me get rid of the extra hydrogen I started with. Oh, now that looks better. There you go. All right. Start with the right number of hydrogens probably helps too. So we're going to do a single bond there. And we'll do that. And we will do this, right? All right. So now when we look at the original carbon-carbon double bond, now that I corrected it there, let's start with the carbon on the left. How many hydrogens are directly attached to that carbon? There are two hydrogens, right? 1 and 2. And on the one on the right, how many hydrogens are directly attached to that? Directly attached to it is 0 hydrogens, yeah? Remember that this attachment is carbon to carbon, right? So again, that carbon up on top has 3 hydrogens, but the carbon in the double bond has no hydrogens. So when you are trying to add something like this in an unsymmetrical addition where you're adding two different things, and it's usually hydrogen and something else like water. It could also be like hydrogen and chloride or hydrogen and bromine. But when you're doing this, there is a rule known as the Markovnikov rule. That is a name. I won't spell it for you. But the rule says that when you're doing this, the hydrogen that gets added on from the water, for example, ends up at the carbon that started with the most hydrogens to begin with. So this hydrogen should end up at the carbon with the most hydrogens. So in this case, our carbon with the most hydrogens to start with is the carbon on the left, which means we should add the hydrogen to this carbon, and the OH should go to the other carbon. Now, when you do that, you create what is referred to as the major product, which is usually the thing that you want to actually do and draw. Now, if you did it the other way, and I'm just going to redraw it, which is your other option. And you added the water in sort of the opposite way, put the OH here and the hydrogen there. You will end up with what is referred to as the minor product. And most of the time, you do want to sort of follow Markovnikov's rule in the major product in this case. And the difference here is actually the names. You actually end up with two different things in this case. So again, we're going from an alkene to an alcohol. Let us try naming this alcohol. Let's start with the top one here. How many carbons do we have? Longest carbon chain is 3 that contains the OH. You could also get it by going this way and up if you wanted to as well. You could have done that. So 3 carbons is based off of propane, but because it's an alcohol, it is propanol, OL at the end of it, like alcohol. OH group is located at carbon number, yep, 1, 2, 3. Doesn't matter which way you go in this case, right? The OH is going to be at carbon number 2. That is 2-propanol. Is there anything else there? There's that guy, right? Which is a carbon group, and that is a methyl group, right? And that is at carbon number 2 as well. So this is 2-methyl 2-propanol in this case, which is an alcohol. What should the name of this guy be? Longest carbon chain is? It is still 3. And again, you could get it the same way. You could go straight across, or you could, again, kind of go upwards to that guy if you wanted to. We're going to just go straight across. So the base of this name is going to be propanol, right? Again, OL because it's an alcohol. But the OH group now is at carbon number 1. We'll give it the smallest number. So we do need a number in this direction. So this is going to be 1-propanol because the OH group is at carbon number 1. And my methyl group will still be at carbon number 2. Yeah. 2-methyl 1-propanol. These are what we like to call different types of alcohols. Do you remember when we talked about carbons, that we could classify carbons as primary, secondary, and tertiary? You could do the same thing for alcohols. You could describe alcohols as primary, secondary, or tertiary. If you remember, the easiest way to figure it out is a primary is attached to how many carbons? 1 carbon, right? Secondary is attached to, and a tertiary is attached to 3 carbon. Alcohols work the same way. The difference is you're always looking at the carbon that has the OH attached to it. Yeah, so you're always looking at the carbon with the OH. Yes. Say it again. The alcohols can only attach to. It doesn't mean that that's their location on the carbon chain. It is how many carbons are directly attached to it. So if you remember when we talked about carbons, there's like a primary carbon, secondary carbon, and a tertiary carbon. That doesn't necessarily mean if you have a tertiary carbon, it's going to be at carbon number 3 always. It just means that that tertiary carbon has 3 carbons directly attached to it. And that's what that means, yeah. So when we look at this carbon here, which is the one that is directly attached to the alcohol, the OH, how many carbons are directly attached to that carbon? It is 3, right? 1 here, 2 here, and 1 more there. That means that this is a tertiary alcohol. Yeah. How about this one? This carbon that has the OH group attached to it is attached to how many carbons directly? 1, which is this carbon right here, right? That is a primary alcohol. Yeah. Question not there. Okay. So if you do this hydration reaction of an alkene, you will produce an alcohol. And if there happens to be a difference in the number of hydrogens that are attached to the carbons in the double bonded carbons, then you do have to kind of follow that rule where the hydrogen coming in always ends up at the one with the most hydrogen that started with. So hydrogen to hydrogen is a good way to remember that. That's where you want to put it. Again, if they have the same number of hydrogens like the first example, doesn't matter. You could put it in any way you like. It'll all be fine. Now, you could also do this type of reaction with something that is not water. So let's just take a look at this here. And you could do this unsymmetrical addition with something like HBr if you like. And this is like hydrogen and a bromine being added. Again, works the same way. We're going to look at our double bond. We're going to make our double bond into a single bond. And now in this case, when we look at our original double bonded carbons, is there any difference in the hydrogens on each of those carbons? The guy on the right has 2, the guy on the left has 2. So in this case, there is no difference. So you can put it wherever you want. If you want to put the hydrogen here, you can, and you can put the bromine there, or you can flip it in this case. It doesn't matter. You can put the bromine on the left and the hydrogen on the right. So you only have to worry about that sort of rule that we just talked about if again, there's different numbers of hydrogens to begin with. Yeah. So in this case, we do get a halogenation. This is sometimes referred to as a halogenation reaction, addition. And we get basically a halogen added to our alkane in this case, in this answer. Now, when we talk about alcohols, again, we do get our alcohols that are derived from water. And since we sort of were talking about primary, secondary, and tertiary, again, a reminder that if you had something like this, this is, again, a primary alcohol because that carbon's attached to one other carbon. By the way, the name of this guy is, how many carbons are on this one? 2. So this is ethanol, OL. You do not need the location because, frankly, it can only be in one spot. It's always going to be carbon number 1 in this case. So 3 or more with alcohols, you got to give that number of location. If you had something like this, longest carbon chain on this one is 3. And we have the OH. So that is going to be propanol. OH is at carbon number 2. That is 2-propanol. That is what type of alcohol, by the way? Carbon here is directly attached to how many carbons? 2. One there and one there. This is a secondary alcohol. By the way, that is 2-propanol, also known as isopropyl alcohol, also known as rubbing alcohol. Yeah, so they're all the same deal here. And then as we saw there earlier, if you had something like this, this is going to get you your tertiary alcohol. 1, 2, and 3 carbons attached gives you a tertiary alcohol. And again, if we were to name this, that is basically what we just had there, I think, on the last slide there. So we have 2-methyl, 2-propanol in this case. And again, tertiary alcohol. So these alcohols are created through a reaction, again, as we saw there of an alkene, through a hydration reaction, and you will produce some type of alcohol. Any question on that there? All right, we'll lay it up there for today.